So far, we have discussed the behaviors of capacitors and inductors when connected to a DC source. Now that we have also talked about alternating current, let us look at the behaviors of these components when they are being driven by an AC source. Let's start off with the capacitor. When driven by a DC source, a capacitor will charge up to the supply voltage, and the current in the circuit will exponentially decay to zero in the process. So, capacitors can be considered as blockers of DC signals. What do you think would happen if we replace the DC source with an AC one? Well, the first thing to notice is that the capacitor will continuously charge up and discharge as the source voltage and circuit current continuously change direction. As you now know, capacitors store energy during charging and release it during discharging. This means that capacitors are cyclically absorbing and releasing energy within the AC circuits to which they are connected. This causes capacitors to alter the phase between the voltage and current within the circuit, meaning that they no longer reach their maxima and zero values at the same time. For an inductor connected to a DC supply, the current exponentially rises to a maximum value as the magnetic field in the inductor builds up. Consequently, the potential difference across the inductor goes to zero, assuming that it's ideal. So, the inductor is said to pass direct currents. When the inductor is connected to an AC supply, the following occurs. The alternating current through the inductor is subjected to a continuous opposition by the inductor, which fights the changing magnetic flux due to the changing currents. To understand how inductors oppose changing currents, check out this video. This means that the inductor will absorb energy from the circuit as the current rises and is said to have been energized. When the current starts to fall, the inductor fights to keep the current constant by releasing the energy stored in the magnetic field. So, like capacitors, inductors are also continuously absorbing and releasing energy in the AC circuit, creating a phase difference between the voltage and current. The absorption of energy by capacitors and inductors in AC circuits is analogous to the absorption of energy by a resistor, with the only difference being that capacitors and inductors give the energy back to the circuit at a later point in time while resistors dissipate it. So, these energy absorptions can be considered as a form of resistances to the alternating current flowing. But since no power is dissipated in these two components, their opposition to AC is called reactance. For capacitors, we call it capacitive reactance, and for inductors, it's called inductive reactance. Capacitive reactance is given by this formula. This is a complex value, where the fraction is the magnitude of the reactance, measured in ohms, and this gives the phase difference between the current through the circuit and the supply voltage. For a pure capacitance, this tells us that the current in the circuit leads the supply voltage by 90 degrees. So, when the current is at its maximum, the supply voltage is zero, and the fact that current leads the voltage implies that the current peaks before the voltage does. Omega is the angular frequency of the AC, so capacitive reactance decreases with increase in AC frequency. This tells us that capacitors offer low opposition to high-frequency signals while blocking low-frequency ones. Inductive reactance is given by this formula. In this case, current lags the source voltage by 90 degrees, meaning that the source voltage peaks before the current in the circuit does. Inductive reactance increases with increase in AC frequency, meaning that inductors pass low-frequency signals while blocking high-frequency ones. These concepts are essential in the design of signal filters. Reactances are treated similar to how you would treat resistance when doing calculations, but always keep in mind that reactance does not dissipate power, but returns it to the circuit at a later point in time, unlike resistance, which dissipates the energy as heat. We will talk about the reactive power associated with the reactances of capacitors and inductors in a later video. That's it for the basics of reactances. Thank you for watching.